So this week's lab was on calculating the mass of a black hole. My name is Zulqar and I'm in lab section MO8. The objective for this lab was to calculate the mass of a black hole, and to do this we were given a data set of a star's position as it orbits around that black hole. And the chief result that I came up with for this lab is that the only force acting on the star was the gravitational force by the black hole, so we are able to calculate the mass using this force. Some important physical concepts to know for this lab was the momentum principle, which says that dp dt equals net force. And it's important to note that the only force acting on the system is the gravitational force, and so dp dt is not zero. Another important concept we need to know was curving motion. Since the star isn't moving in a straight line, it's orbiting around the black hole, we have to take into consideration the perpendicular and parallel components of the net force. So the code I used for this lab is right here. I highlighted the mass of the star that I was given, and the delta T is 86,400, which is the number of seconds in one day. And then the X and Y positions that were given to me are imported from this Excel file right here. Everything in the A column that I highlighted is the X position, and everything in the B column is the Y position. And that information is also used right here to calculate the velocities, the X and Y respectively. And then throughout the whole program, it goes through this while loop, and with each step in the while loop, it updates the position and the velocity depending on what X and Y position is at. So the actual physics behind the code is right here. So the first white block is the momentum principle. So as you see, the initial and final momentums are calculated, the velocities are calculated, and right here it says F net equals dp dt, which is of course the momentum principle. And then we had to break that net force into a parallel and a perpendicular component. And so the parallel component is equivalent to your change in magnitude of momentum over t times your unit vector of momentum, and that was calculated in this code. And as you see, the F net parallel is equal to dp dt parallel, and the same thing with your perpendicular component. dp dt perpendicular is equal to your F net perpendicular, and that was calculated just by subtracting your parallel from your dp dt, because that's what the equation says. And as you can see in the red dashed box in the bottom right here, that's where your actual, that's how you calculate your perpendicular component. And so like I said earlier, the objective was to calculate the mass, and by doing that I used the gravitational force because that's the only force acting on the system. This is the equation for calculating that, and then I rearranged it to this equation right here, which is simply just your force, which in this case, is equal to your dp dt, which is calculated throughout the loop. It is multiplied by your distance between the star and the black hole squared, divided by your g constant, which is 6.7 times 10 to the negative 11, and that multiplied by your mass of the star. And from doing that, I got the mass of the black hole to be 2.985 times 10 to the 31st kilogram. And I wrote that in my actual code like this. I just made it bigger for you guys to see. So I'll just run the program really quick for you guys to see what it looks like. So there we go. That was the yellow ball is a star, and the black hole in the middle is of course the black hole. So that was what the mass of it was, and I got it to print out the mass of the black hole, which is right here. And then I'm just going to run it again for you guys to see the arrows. Just fair warning, the blue arrow is your arrow that represents dp dt, also the net force. The green arrow represents your perpendicular component of the force, and your red arrow represents the parallel component. And it does go pretty fast, so I apologize if you guys can't see it that well, but here we go. So as you can see, the red arrow got small because that represents your change in speed of the star as it goes. So like if you saw properly, as it got to the black hole, it got bigger, and then as it got away, it got smaller. And then this blue arrow, which is the arrow representing your dp/dt. It's pointing towards the center, because that's how the change is. And then perpendicular force always points towards the inside of the kissing circle. And so for the what does it mean part of this lab, the 3 questions were how do FNet and dp/dt relate, as well as the perpendicular and parallel components relate. They're all the same quantity. We know this based off the momentum principle. They're related in the sense that their numerical values are the same, but they're different in the sense that they represent relationships between 2 different things. For example, force represents the relationship between mass and acceleration, whereas dp/dt is a change in momentum over a change of time. And then the what if question just asked if we were to put in a new black hole but nothing else changed. So the star just moved in the same direction, in the same orbit as it did, all the positions were the same. Could we tell a difference? And I said no. And that's because if you look at the equation that I used to calculate the mass, nothing in the actual equation changed. So that doesn't really affect too much the change in the mass, because your force is still the same, the dp/dt is still the same, the distance between the star and the black hole is still the same, the g is always constant, and the mass of the star is still the same. So there wouldn't be much of a difference in the mass.